Prof is in.
You guys.
Hello. How is everybody today?
Good morning, Prof.
Bye.
What you guys been chatting about?
Just checking on each other.
So, talk to me about what you're learning in this course. Do you feel like you're learning? What kinds of things are you learning about?
I was going to say, wait, can you hear me?
Yeah.
Oh, yeah. Okay. Really, with it being an introductory course to all things climate change, I like how we kind of started with. I like the how the course was composed of how we started talking about what climate change was, and as we progress through the course, we will learn. I mean, we've learned um, ways of essentially understanding climate change, how it works. And now we're towards the end, and we're somewhat coming up and devising ways to, of course, develop adaptation and mitigation efforts. So I really enjoy how the course was structured, starting with climate change, the smaller intricate parts of it, kind of explain it and kind of laying the framework for it. And then now, kind of actually thinking towards, okay, how do we, go about this problem or situation?
Good. Good. How do others feel?
Yes, actually excited about so far what we've learned, the new knowledge about epigenetics, the geoengineering, and how they are actually being used in biotechnology in solving the current issues, and actually knowing how the events of climate change have been unfolding from different cyclones and droughts and all those events, how they have just been on the extreme side, actually was a thing that I've been interested in monitoring and concerned about. But at least this has drawn my interest to know that these events are taking place every day, and they're actually affecting both every living things, humans and plants as well. And there are ways we can actually do, though adaptation is like difficult, it's expensive, but these are ways we can actually work with the adaptation and the mitigation aspect. We really need to work on them and to bring a solution. It has been a great lesson knowing the sequence of things and what to do.
Good. Good. Anyone else?
Hello, Prof.
Yeah, Shepard.
Yeah, for me, I can say that climate change, it is something that was a little bit lacking in the agriculture sector. So I think at the end of this program, I will be able to contribute much to, for example, in agriculture, people they've been they've been using heavy use of chemicals, which have got an effect on the environment and on the climate at large. So by this program, I believe it is going to help me come up with the strategies to incorporate climate change aspect in the agricultural sector.
Good, good. Yeah, and this course in particular, the Intro to Climate Change, this is just the beginning of this program. And the idea is so you can get a solid understanding of what's leading to climate change, what all the factors are, where the carbon sinks are, how all of it works, right? Because I think it's important to have that general understanding before you dive into specifics on how to use biotechnology, for example, to help in agriculture and stuff, because you want to know what the general impact is going to be on the larger problem, right? And any solution we come up with, we hope then will be replicated as part of a technology that's used all over the place so we can multiply its effects. But first, I think we need to understand the generalities and such. Now, do you feel like you already knew the stuff that we've talked about in climate change in terms of like how it works and how it heats the planet and all that kind of stuff, or have the details been new? Trying to get a gauge if you already came into this and you're like, well, I really haven't learned all too much. I kind of knew what climate change was coming into the class versus now. And Desire, why don't we start with you?
So I had just a general idea of climate change, and it was mainly attributed to fossil fuels back then, but I didn't know like I didn't have the in-depth knowledge on how it actually contributes to climate change, and the climate models was something that that was eye-opening, and I did learn much. And now that we're looking at adaptation and mitigation measures, it's something that I can relate with, and I can be able to use the knowledge for the project that I'll be embarking on.
Okay. Now, Mungo?
Yes. Probably I will say that I had a general understanding of this particular effect of climate change, especially from my geography background, but I have been able to learn a lot, which is totally new. And also in terms of what we are doing in genetic engineering in relation to climate change, those are absolutely new ideas which I'll be able to apply. Probably to advance the knowledge that I had in my previous program of One More Science.
Fair enough. Fair enough. Fair enough. Yeah, like we're not really coming up with solutions here. We're going through a lot of what solutions are the general categories of different solutions, right? When we get later into the program, I think next year about this time, you'll be taking the mitigations course, which goes in a lot more specifics. We'll do case studies on various biotechnology projects that our folks are currently working on that are considered solutions, or at least things to help the problem. So with that said, let's see, we had been talking about, was there anything else anybody else wanted to say? Brenda, Zakiu, I don't think you had a chance to say anything.
Okay, sorry, I was late. So I'm not sure what you were talking about, but I have a question which is not related to the lecture anyway. It's about our exam. I wanted to know, because for me to be given study leave and be able to take some days for me to write the exams, they need the timetable so that they could allow me some days. So I would like to know, like, what's the timetable like, and when are we writing our exam?
Okay, exams will probably happen in the first week of December, and we can set a date in there, but I think somewhere around like December 3rd or 4th, I think is when we're going to do the final exam. And I can have a written exam, but I'm slightly tilted towards because it's the first time we've run this course. I really like how we've been doing this. I'm slightly tilted towards doing oral exams and talking through because I think I get a better gauge of what you do and don't know, work through a problem and stuff like that. So I'm kind of, well, what do you all feel? Would you prefer an oral exam, or do you like the written exam? Do you like the electronic exam?
By an oral exam, what do you mean? Is it a flip
No,
record
it would
or
be one-on-one. We do a Zoom, just me and you.
okay.
So how do folks feel about that? Any preference one way or another? I've always found that it's better to rather than completely design the course just a certain way, I like to get the input and feedback from students to find out, you know, what works for them better. The thing I don't necessarily like about a written exam is it has to be open book, right? Because there's no way to correct for not being an open book, because people could open a book and they're, you know, they got their phones. The software to try and make sure people aren't looking at other things doesn't really work all that well, because you can have multiple devices. So open book exams tend to be longer. They test you more on how you use the knowledge rather than, you know, what's the current ppm of carbon dioxide in the atmosphere, you know, how much carbon is held, you know, in the oceans, how much carbon is held in the atmosphere, that kind of thing. Those numbers are good on an exam that you have to take right there, but on an open book exam, all you're doing is looking up the number and writing it in. I trust that if you're graduate students, everybody can do that. That doesn't tell me, you know, if you've learned anything. And so those become, okay, now work out a problem where we've changed, you know, this amount of carbon dioxide in the atmosphere and what kind of, you know, temperature change does that lead to? And then you got to work something out. So, you know, with one-on-one oral exams, I just ask you questions and see if you know the answers, right? You know, how much carbon is in the oceans? How much carbon's in the atmosphere? You know, tell me about the carbon cycles, for example. Now, many of the questions I'll ask, not all of them, but I'd say at least 60% of the questions I'll ask are ones you've already done Flipgrids on, because I do Flipgrids on the most important stuff, right? But there's a lot of details we've covered that we haven't gotten to do a Flipgrid on. So any preferences you want to mention?
Okay, I say let's go for it. At least this
Okay.
makes us really know our stuff. Yeah, I don't know about others.
Okay, so we'll see. I'll probably decide in the next week, and I'll let you know as soon as there's some kind of a decision on that. Any other questions before we get talking more about this fun mitigation stuff? Okay.
Hello, Prof.
Yeah, go ahead.
Yeah, for us with the desire, we're still having challenge for ethics. They are being given assignments and also some tests we are not able to access.
Right, if it's in Moodle, right, then it becomes difficult, right? Gotcha. And that limitation I know of right
Yes.
now. And so that I'll take into account. I'll make sure you've got a way to do that without that worry. Okay. So let's try and get back to some of our course material. We were talking about mitigation. So I asked this question before, but hopefully I'll get a different answer this time. What's the difference between mitigation and adaptation? What's the key difference?
Mitigation deals with the lowering of greenhouse gases.
Yes, that's what I'm looking for. It's got to be something that lowers greenhouse gases. Now, what was the technique that we taught? What are our different techniques for mitigation?
That's the use of biofuel. Biofuel, these are the renewable energies.
Mm-hmm. Right. So the idea is as we switch from fossil fuels to renewables that have zero net carbon release, and I say net because remember biofuels They do release carbon, but there's zero net release. But as we go from a positive release to zero release or net release, that's a mitigation because it's bringing down our emissions. So anything that brings down our emissions is going to be mitigation. It's decreasing the cause of the problem, right? Now, we talked about a third option besides adaptation and mitigation. We started talking about geoengineering. And so what was the method of geoengineering that we talked about last time?
Manipulation of the climate.
How? Specifically, how manipulating the climate by what means?
By putting in.
Okay.
Anybody remember last lecture? What we started talking about?
Okay, I think it was about releasing what is that? Creating
Release
sulfur injection into the.
Yes, Naimango, right. It's injection of sulfur into the atmosphere.
Sulfur into the stratosphere.
And so how is it injecting sulfur into the atmosphere, into the stratosphere, going to do anything for our climate? It doesn't sound like a good thing. It's sulfur.
According to how it was explained, it does help in reducing temperature. However, with the effect, it comes with the effect of it would disturb the like rainfall, the process of rainfall. So you'd find out that yes, the temperature might reduce, but it will also come at a cost of having altered like rainfall patterns, where some places would they would experience drought, whereas others would have more rain. And we did go in and like looked at individual countries wherein they had to agree on such a thing, but with the effect of certain places having like drought, it would cause chaos or conflict.
Okay. Okay. So how specifically does injecting sulfur into the atmosphere change anything to do with the temperature?
It creates a reflective, well, has reflective properties, which would in turn increase the albedo, because the light that will be coming in from the sun, of course, through the earth, the atmospheres, will be reflected with the addition of the sulfur into the atmosphere, and of course that would increase the albedo and decrease temperature. Or that's the theory. Rather, that's the theory.
Right. So the big idea there is you're creating these aerosols, which are reflective, and they're really tiny little droplets. And so they have a negligible fall speed. In other words, they just kind of float around up in the stratosphere. Our gravity doesn't really pull on them all that much. And so they stay up there for a long time. Anybody remember about how long they stay up there?
4 years.
4 years.
4 years.
Okay. I'm very detail oriented. Okay. I like everybody to know those specific details. You're going to see that to the max when you get into genetic engineering 2, and we talk about protein structure. You're going to be knowing different energies and all sorts of things just at a snap. So I think these details are always really kind of important. One of the things I want to share with you here, this is a great article. This is by in atmospheric chemistry and physics. And oh, where'd it go? Come back here. In atmospheric chemistry and physics. There we go. And so they're exploring the idea of using sulfur and putting it in the atmosphere. And basically their conclusion in this article is we need to do a lot more study before we do it, because we don't really understand what the regional implications are. As people just mentioned, one of the problems with solar radiation management in this fashion is we really don't understand how it's going to affect precipitation. They're trying to draw maps to give us an idea of what areas. Let's see if I can bring up some of these maps. They go through how they build their models. They look at temperature distributions. They look at if you were to add sulfur, what those temperature distributions, how they will start to change. And then they try to make some regional predictions on whether, after looking at wind speed, they try to look at surface air temperatures and changes in precipitation that you might expect from doing this model. And there's a lot, we have no way to confirm this, right? Because these are just models. So we don't have any, let's make the change and then read the data to confirm that the model is working, right? The closest we have is when we get volcanic eruptions, to give us some idea of, how long, that's how we know how long it stays in the atmosphere, by the way, is from volcanic eruptions. Usually the stuff stays in the atmosphere for about 4 years. So solar radiation management, the one thing that folks like about it is it would have an immediate effect in terms of changing our albedo, which will affect energy in. But you've got to remember that it doesn't change the amount of CO2 in the atmosphere. So it's not really a mitigation, right? It's putting a Band-Aid on the problem. And as much as, we reflect this sunlight off, we're not getting rid of any sort of carbon dioxide. And so, as we mentioned, if you stop putting in the atmosphere, within 4 years, it will all go away. And I tried to show you this graph of, if we're steadily increasing carbon dioxide in our atmosphere, and then we start solar radiation management by putting in just enough sulfur to increase the albedo just enough to offset the rise in temperature. And I think I actually worked through a couple calculations of showing, how by increasing the albedo, you can bring the temperature back down to what it originally was before some kind of greenhouse gas effect. Okay, so if we add this sulfur into the atmosphere to counteract the warming due to increased greenhouse gases, if we stop within 4 years, the albedo change will go away, and then there's still all that CO2, and so now we're hitting really rapid warming. And the worry is that the rapidity of that warming would be much more catastrophic, because things don't adapt when things change suddenly. And so it could create a lot of problems. And so we'd really have to think carefully of how do we end it? When do we end it? Do we do it forever? Are we going to still keep burning greenhouse gases and putting them into the atmosphere? Are we going to bring them down first before we end our stratospheric sulfur injection? These are all things that many countries would have to agree on. And if there are changes in precipitation, we really have to think about which countries are going to be affected the most, because we don't want wars to be started over what one group is doing and how it's affecting another group. We already have enough of that with climate change in general, because again, as we've mentioned, most of climate change was caused by the more affluent because they have a higher carbon imprint. because they use more stuff, they use more services, which use more energy, which in order to generate that energy, we burned fossil fuels. So stratospheric sulfur injection is a temporary band-aid to stop the temperature from rising beyond a certain point. And that may be necessary. With the amount that we're putting in now, we may get to points where if we don't do it, there are other catastrophes that are far worse that are going to happen if we don't do it. If we have large swaths of land that become completely unlivable, well, that's a lot of people that have to move to where other people already are. So there's lots of things to consider. And probably the biggest worry about rising temperature is the melting of the Antarctic permafrost, because the amount of CO2 and methane that would be released would be truly catastrophic. Then we're talking about a 9-degree warmer world, which is not something any of us want to see. And we just have no hope of dealing with it. So you have to think of solar radiation management as a potential thing that can be used. Hopefully it's a last-ditch effort, but we might need to go into that toolbox. Preferably, it would be nice to be able to pull the CO2 out of the atmosphere, right? Just get rid of the problem, take it out. And indeed, there are various projects where people are trying to do that. So this would be considered definitely a mitigation strategy, because you're lowering the amount of CO2 in the atmosphere. And so there's a lot of different ways one could set up these plants to do stuff. So a lot of folks who want to continue to burn coal, what they try and do is capture the carbon dioxide kind of at the source. So when they're burning the coal, they're trying to offset the carbon emissions by taking that CO2 and sticking it, capturing it, putting in a pipeline, and maybe pumping it under the ground or mixing it with concrete. That's another option. So it isn't released back into the atmosphere. So that's the idea. There's a lot of projects that have been around for a little while that do this kind of stuff. So, the Alberta Carbon Trunk Line project. This project here is probably the world's largest carbon capture system, with a 240 kilometer pipeline. Again, it's trying to capture these gases as we burn them. And this captures about 14.6 million tons of CO2 annually. Does that sound good? Okay. There's the Quest Carbon Capture and Storage Project. Okay, this is in Canada, in Alberta, Canada. This is done by the Shell Oil Company. It's no longer in operation right now, but they claim that they're refurbishing it and expanding it. And this is capturing carbon from steam methane units, and they're injecting that carbon into porous rock formations. They claim to have stored about 3 million tons of carbon dioxide into these porous rock formations between 2015 and 2018. Another well-known one is the Boundary Dam Power Station, again in Canada. This was completed in 2014. This is a coal plant, okay? And after combustion, they're capturing the CO2, okay? And this one stores and captures and stores about 1 million tons of CO2 per annum. There's some other ones. There's the Great Plains Synfuel plant. This is another very large one. Between 2000 and 2018, they say they've captured and stored over 30 million tons of carbon dioxide and injected it and sequestered it permanently. A much newer one is a coal power station in China. This was just completed in 2021. Again, it's a carbon capture and storage, and it's a coal plant. So they're burning coal, but they're trying to capture some of the stuff. And they said they're lowering their emissions from their coal plant and storing and capturing about 150,000 tons of CO2 each year. And they say that they've reached a 90% capture rate, which is quite high. A lot of these other capture technologies that are mentioned are probably in the 60% range. And how much, if it's at the coal station, how much they do. There's also the Geoengineering oil. Is this the same one? The Geoengineering oil field. This is also in China, a little bit older. It's not quite as efficient, but they say about 0.6 million tons of CO2 that they're capturing and putting into the ground. Okay. Do these numbers seem pretty big?
Only the first facility, to be honest. They seem big in in theory, but I feel like there's a lot more, of course, CO2 in the atmosphere over hundreds of thousands of years, and the numbers, and in theory, they seem large, but yeah, I wouldn't believe they're doing a whole lot outside of the first.
Okay. So besides these plants, these coal plants and oil plants for trying to capture what's being released while they burn these fossil fuels, remember, in that case, they're not really taking stuff out of the atmosphere yet. They're stopping some more from going in. Okay. So there's a biology project, a biotechnology project trying to use autotrophic eukaryotes, trying to basically, Pichia pastoris will grow on CO2, and so it builds biomass, but they have no data yet on exactly how much a potential facility could trap for CO2. But if you look at all of the projects, all of the carbon capture projects listed, and there's probably about, I think, 47 different carbon capture projects that's listed in one of the latest IPCC reports. They capture about 40, at least in 2021, they were capturing about 49 million tons all put together of carbon dioxide. Is this a lot? How does this look as a solution to you?
Prof, hello. I'm just wondering if all these were actually captured, why are we still facing so much changes in the climate?
That's a great question. Can anybody answer that one?
Okay, so from my own thinking, this is a great number, but it's a global thing, like global change. So like we have seen most of these projects, they're in Canada and China, and yet all over the world, all the continents are doing activities which release carbon dioxide into the world, and these projects are trying to stop adding more carbon, but There are only small projects. They're few as compared to the amount of carbon which is still being released by other continents, because global change and climate change is being contributed globally from everywhere. So that's what I think.
So you say it's a small amount relative to what's being released. Can anybody tell me how much carbon is being released by the burning of carbon of fossil fuels?
10 gigatons.
Okay. Where do you get that number from?
I was reading a textbook. I was actually reading about it today.
So the latest numbers I have for 221, around 36 gigatons. And 2022, another 36 gigatons. So all these carbon capture projects in total are probably capturing around 0.18%. So a tenth of a percent, maybe 0.2%. So these carbon capture projects are really, really, really tiny. Okay. I don't know if any of you were able to look at the article I sent from the New York Times, but just a few days ago, they had this really cool article in the New York Times about a commercial plant starting to pull carbon directly from the air. Okay, and the way that they do this is they have these trays of rocks that will react with CO2 and incorporate them into the rock structure. And it's really neat. They have these trays. It comes to the CO2 and they're capturing carbon. And let me see how much they said they were doing. I think they said, I got it right here, carbon capture. I was trying to put it into this. For their facility, they were getting about 5 tons of CO2. Tiny amount, right? Really, really tiny amount. And so, and this is expensive. They're at a cost of about $600 per ton of carbon, which if you think of how many thousands of tons of carbon we need to do, that's way too expensive. Carbon capture projects are very expensive and tend to get small amounts of carbon. It's great to have them, but we really need to ramp up the technology if we want to increase things. Now, I pulled some data off the web that I could find because I was curious how much CO2 you need to add to the atmosphere to raise it by 1 part per million. And it seemed to suggest around 2.3 gigatons. And so I looked at what's the data from year to year in terms of what the ppm increase was in our carbon dioxide levels. And remember, in an earlier lecture, we talked about doubling carbon levels, right? We're at around 400 ppm right now. If we double it, we were expecting, does anybody remember what the temperature rise that's expected for a doubling of CO2? It's a really important number to remember. If you double the amount of CO2, how many degree rise do you expect, considering all the feedbacks?
About 4 degrees Celsius.
The range I think was between 2.5 to 6. 4 is good. I think the settled on number is around 3 degrees. So you're pretty close. And so that means, you know, if we're at around, you know, a little over 400 ppm, we have till 8 ppm, right? 800. And this is the amount that we're kind of adding in each year. Now, what was surprising, if you only need about 2 gigatons to raise it by 1 part per million, if we're throwing out 36, anywhere between 10 to 36 gigatons, why aren't we seeing the ppm go up so much higher? The parts per million. Why aren't we seeing the concentration of CO2 just skyrocket even further? Because if 2 gigatons will raise it by 1 part per million, and we're releasing, if you use the book number 10 gigatons, so that'd be going up about 5 parts per million. If you use this number, that'd be about 18 gigatons. And so you'd be going up by about 9 parts per million. Why aren't we seeing such a ppm increase with the amount of CO2 that we're releasing in the atmosphere? Why do those numbers not match?
I would assume through the different means we have, such as the land to carbon, well, not land to carbon, but the ocean with
what do we call that? Going from atmosphere to land, we call that the atmosphere to land biosphere sink.
the atmosphere to land biosphere.
Mhm.
The atmosphere to ocean biosphere, the atmosphere to of course rock biosphere.
Right. Right. Well, just the rocks. Yeah, to the rock reservoir, as we'll call it. So it's the atmosphere to ocean. The ocean is very large. So we think about 25% of 25 to 35% of the CO2 we release into the atmosphere is going to go very quickly into the oceans. And about 20%, 25% is going to go into the land biosphere. So those are 2 really big sinks. And so that's why all the stuff we put in the atmosphere doesn't immediately rise the atmospheric levels of CO2 by as much as we put in, because it's taken out, you know, into these other sinks. So that's good to know. I'm glad you answered that correctly. Thank you. Any questions on any of this kind of mitigation or adaptation stuff? Because we're going to kind of go into, we're going to start getting into policy and, you know, what different countries are doing, and the Paris Climate Accords and that kind of stuff, and the economics, how to solve it through economics. So anything about this section you want to ask about? By the end of this course, you'll know about just about every example of people trying to fight climate change. You know, whether it's through various adaptations, various mitigations, geoengineering, all these kinds of things. I want you to have a wide knowledge of what's out there, because you need to be experts in climate in the field that you're going into in climate change. And hopefully after the end of this course, you'll kind of be halfway there. Okay, great. I'm going to reach out to you. I'll have a lot of free time tomorrow, so I'll be reaching out to you. If you have any questions and you want to do a private Zoom at any point tomorrow, let me know, because I'll have some time at my desk to do that. We could just, you know, chat. If that's what you want to do, we can talk about course material. Just shoot me an email and we can set up a time if that's something of interest to any of you. Okay, everybody, have a great day. And I will talk to you soon. Bye-bye.
Thank you, Prof.
Bye.
Thank you, Prof.
You're welcome. It's been a pleasure.